This is Unit 3, Video 9. In this unit, we will talk about molecular polarity. So the big discussion will be about polarity, a very, very important concept when you want to understand how molecules, how the shape and so forth of molecules affects their properties. Now, we talked about polarity in terms of individual bonds. So we said, for example, we talked about the electronegativity difference between two atoms, and we said that if there is a difference, then the bond was polar. So for example, here is the element carbon, or the atom carbon, here's the atom oxygen, and here's a bond between them. Now this is a double bond, but what we do is we check the electronegativity difference, and oxygen being very electronegative will actually pull the electrons closer to itself, creating a polar bond. And there's a slight negative on this side, and there's a slight positive on this side. Now that's represented by this arrow. If you take a look, there's a red arrow here that actually signifies a polar bond. And the way you do this is you have a positive on this side of the arrow, the side that has the less electronegative atom, and the head of the arrow represents the negative side of the more electronegative atom. So you can see that this is a polar bond. And we call these bond dipoles. You can actually measure this, and you can talk about the dipole moment of the bond itself. You can give it a measure. You can, 1.7 or something. You can actually talk about that from the electronegativity difference. And then what you can do is consider the entire molecule, because polarity, in order to understand polarity, you have to think about how the bonds are arranged in 3 dimensions around the molecule. And then those polar bonds will come together to give you a whole polarity of the whole molecule. So here it says just because the molecules possess polar bonds doesn't mean the whole molecule will be polar. In the case of carbon, you have an exactly same bond going this way and the exact same amount of polarity in the opposite direction, so these two actually cancel each other out. So because these two bonds, the polarities cancel each other out because they pull in different directions, the overall polarity of the molecule is 0. This is called the dipole moment of the molecule. What you see below is actually a little picture called an electrostatic potential map. Fancy word. I'm all for fancy words. Electrostatic potential map. And what this does is it essentially shows you blue would be high electron density, there's a lot of electrons here, and then red would be low electron density, so very few electrons here. Oh no, that's backwards, apologize. Oops, nope. This is high electron density, and blue is, sorry, so this is high, and this is low. Right, red would be high electron density, and that would make sense because the oxygen's on the outside, that's the one that's more electronegative. Alright, hopefully that makes sense. We're not going to do too much with these electrostatic maps, but you'll see them. You can actually draw one for every single molecule. Color codes the electron density areas. Okay, so now by combining individual pole or dipoles or individual bonds, we can determine the overall dipole moment or the overall polarity of the molecule. So that's what we're going to do here. So here it says if the individual dipoles cancel each other out, the molecule will be nonpolar. If the molecule is asymmetric, that means it's not equally distributed, the bond dipoles will not cancel out and the molecule will be polar. And this is famously displayed by water. Now water, we always draw water like this, and then you have yourself a pair above and a pair below, electron pair above and below, and eventually this becomes bent. We know that the shape of this is bent, and that's why water molecules are always drawn like this. You have 2 electron pairs pushing down on the bonds. Now, because you have a polarity between the oxygen and the hydrogen here, oxygen again is more electronegative, so you see this polarity arrow pushing toward the oxygen. There's a positive side on the hydrogen, a negative side on the oxygen. You actually have a lot of electron density here. The electrostatic map shows a big red area here. That's a lot of electrons on the top. And because you have the same thing happen between the other 2 atoms, these 2 do not cancel each other out. In fact, they pull toward the top. The whole polarity of the molecule pulls up here. And in fact, this overall shows you that the molecule is polar. There is a dipole moment. There's actually a partial negative charge up here and a partial positive charge down here. So this water molecule is polar. And it's polar because technically it's asymmetric. The bonds themselves don't cancel each other out. So this will be important. Alright, So let's take a look at the next few molecules. Let's take a look at some examples. So here it says, go ahead and determine whether the molecule below are polar or non-polar. Now I've drawn them for you so we can analyze all these shapes we've talked about. And then we'll do the example that has actual molecules themselves that you have to draw out. So this first one is a linear arrangement. Now you'll notice that the answer is kind of given to you if you take a look, because there's a polar arrow showing that electrons are pulled toward the chlorine. So this definitely is polar, because you have a negative side. It's technically a partially negative side. We use this little letter to designate partial, being partially negative, and this is partial positive. So that is definitely a polar molecule. If you take a look at a trigonal planar arrangement, this is actually going to be nonpolar, because all three of these go in opposite directions and cancel each other out, as long as all three of these are fluorines. Now notice that if they were not fluorines, say if one of these was a chlorine, then the molecule will be polar, because that would change the amount of pull of these bottom ones as compared to this top one. So right now this is nonpolar. We can say NP for nonpolar. The tetrahedral arrangement, the third type, is all going to be nonpolar, because all four of these again do the same thing. They point to opposite directions, and the four chlorines will create, they cancel each other out. This will also be nonpolar. Now in contrast to this one down here, this one would actually be polar, and the reason for this is because the chlorine at the top creates a different pull than the carbon and hydrogens at the bottom. But in fact the carbon and hydrogens create a nonpolar bond. If you take a look at the electronegativity difference, you'll see that here this is so small that it technically is nonpolar, and that's why you don't see an arrow, a red arrow like you do on the other structures here. The electronegativity difference between carbon and hydrogen, carbon is 2.5 and hydrogen is actually 2.1. So what happens is the difference here is 0.4, and 0.4 just falls into the category of nonpolar. So in fact, hydrogen and carbon don't create any polarity. In order for the whole molecule to be potentially polar, you have to have at least polarity in the bonds themselves, and we'll show you a few examples of this. So this molecule is polar just because of this chlorine. So this chlorine pulls up, so it is polar. And the last one here is NH3. This one is asymmetric, as we see, and it's asymmetric because there's an invisible pair of electrons up here. So this will be a polar molecule because these three do not cancel each other out. So this would be polar as well. So hopefully just visually this makes sense, and let's go ahead and do some examples. We'll do the practice together. Let's do these 5 molecules and determine their polarities. Now the very first one is actually between two different elements, bromine and chlorine, and as long as there's an electronegativity difference between them, this will be polar. So if we draw the structure itself, it will look like this, and really what you're looking at is the bond itself between the two atoms. So as long as this difference is big enough, and it is big enough to be polar, then we call this whole molecule polar. And actually the polarity is toward the chlorine. So what you could do is you can draw a little arrow like this showing which way the polarity goes. Alright, the second one, CCl4, just has a carbon in the middle and chlorines on the outside. And you can fill the chlorines with octets, and this should match. In this case, you have 4 equivalent bonds to 4 equivalent atoms, so they will cancel each other out. So all 4 of these, remember, go in all 4 different directions, creating a tetrahedral arrangement, and they cancel each other out. This would be nonpolar because it's symmetrical. NF3, the next one, will actually have a nitrogen and 3 fluorines on the outside, and there's an octet around each fluorine, and nitrogen does have enough to create his own octet. In this case, it actually is trigonal pyramidal. These fluorines actually bent downwards, and so the fluorine here, being more electronegative, will pull the electrons closer to itself. So in this case, this is how it goes. The polarities actually pull downward. So this will be polar, and what you would do, you would actually draw an arrow pointing downwards, because overall the polarity points down, because fluorines are more electronegative. So this one's definitely polar, and those are the polarity designations. Okay, this next one SO2, if you take a look at SO2, we'll draw him down here. SO2 actually contains a single and a double bond, looking like this. And because of resonance, we should draw a second molecule. The molecule looks like this. Oops, extra pair of electrons. In this case, what you have is you have yourself equivalent bonds to the left and to the right. So both of these are actually equivalent bonds, which means, do they cancel each other out? Well, no they don't, because the molecule itself has a bent structure. Because this pair of electrons on top pushes these down, you actually get yourself kind of like this. Since it's bent, it does not cancel out, and the bond polarities pointing downward would not cancel each other out. Overall, there will be a bond polarity pointing down to the molecule. So this is really the designation that you will draw. And in this case, you will say that this is also polar. And then it's the same thing that you've seen before, because it's asymmetrical. It's not evenly spread out in terms of the electron domains. Well, I'm sorry, in terms of the molecular domains, it'll be polar. This last one, you can maybe even see, just without drawing it, that it should be nonpolar. The reason it'll be nonpolar is because you have the 6 atoms going to opposite directions, and that kind of is the maximum amount of atoms that you can have, electron domains that you can have. So you have a sulfur, and you have the fluorines all the way around the outside, and each gets an octet, full octet. Fluorine won't be sharing any electrons. And because these go on opposite sides, they will cancel each other out. Each one of these dipoles here will cancel out each one of these dipoles here. That's the way you can think about it. And because everyone cancels out, this molecule is actually nonpolar. Okay, so we'll do a lot more of this in class to practice, but this completes for us the 9th video of the unit.